In this video, I'm going to discuss how to use a program called CrystalMaker. It's a great visualization program for exploring the three-dimensional structure of solids. So first of all, CrystalMaker has been around quite a while, more than a decade. Um, it continues to have a free demonstration version. How long that'll last, I'm not sure. After this video goes viral and 10,000 people grab the free version, maybe they'll change their policy. But for now, you can just Google CrystalMaker free demo, take the link. I'm a Mac person, so then I just grab the one that's available for the Mac. No cost. They're trying to show you some of the features of the program. So after you pull it up, within the program, it's going to, when you open it, it'll ask you, do you want to unlock additional features, or do you just want to explore the demo? There's a lot of functionality if you just explore the demo. So I'm going to close that part of the window. These are all different files within CrystalMaker that the software designers are using to illustrate different features. Some of these, I think, can be really effective within your class. I'm going to open up this one for gold. So let me show you how the program works. So first of all, by clicking on Inspector, I'm going to get rid of that information that was on the right-hand side. Within CrystalMaker, you can rotate around the structure. That little hand designation, when it's on the hand, that means it's free to rotate around. Under Model, both the ball and stick and the space filling are useful representations. This is the ball and stick representation for gold. So what I showed you there was, if you click on the inspector, what that does is it gets rid of this information that was on the right-hand side, makes it full screen for you. By clicking on the hand, that allows you to rotate, to spin it around. By clicking under model, we could choose, do we want to look at ball and stick or space filling? There's other model representations too, but I find those two to be the most useful. So here I show images. Is it a ball and stick, or is it we're using the space filling? Great question for the students. Well, what would be the advantages and disadvantages of each representation? If you say, well, which one is more correct? I think the space filling is a more accurate representation for what one finds with gold. But you need to sort of change the zoom. You've got to make the atom small if you really want to get a better sense, I think, of the structure, of the crystal structure. In this case, it's face-centered cubic. The lines that are being shown there as bonds, don't let that boss you around, okay? I'm not letting that tell me, oh, well, that is what the bonding model is in a metal. That's not my picture for what's taking place within a metal, but the program is just trying to show with that where the atoms are found with respect to each other. Back within the program for gold, I'm going to switch it to the ball and stick representation. Let's look at that on that side of the unit cell. Students always wondered, well, how can something be partially in a unit cell and partially in a neighboring one? So I'm going to make a supercell. I'm going to add another unit cell to the side. This is a great way to see how when you have the two neighboring unit cells, that atom was found in both of them. That was adding one additional unit cell. If we go to unit cell, generate supercell, we can, instead of adding one, let's make it where we have 2 by 2 by 2. Okay, that gives us a lot more. Let's change the scaling on that. So we can zoom out then. Notice how when we rotate this, there's particular times when it's aligned and we can really see it become symmetrical. My daughter used to play with, she used to think this was a video game. She would take it and spin around the crystal structures until they almost magically became aligned. Really powerful visual that you get within this program. So within that, what I did was I went up to transform, chose unit cell, and found that I could now generate a supercell. I could add additional unit cells to the visualization. Be careful with how many you add there, because as you see, if you add too many, it's going to become a really, really big file, really big, a lot of atoms within that. So I usually do it in stages. I don't make it, well, let's go 10 by 10 right from the start. That's going to be crazy. But you can also then, of course, rescale it back. Now, let's look more closely at the structure of gold here. Metals often adopt what are called closed pack structures. They end up having a maximum density because the atoms are as close together as they can be, and that leads to a coordination number of 12. Let's explore that within the CrystalMaker. So I'm going to make a cluster now. I'm going to click on cluster and look at what is around that particular atom as a function of distance. As the distance gets larger, it's changing the scale there, but it's showing what would the atoms be like in that next layer out. If we move to the nearest neighbors that we have, this is a really good way to look at what the coordination number is. So we see around that central atom, there's a total of 12 different neighbors around it. Clicking on the arrow within that, we can see what the distances actually are. This is showing how the metal is adopting a stacking arrangement of the layer at the bottom, the layer at the top, and then the layer at the very top returns to the one that was below, that was the initial. It's called an ABA layer. This idea of using the cluster function to explore what the coordination number is, I think that's a really helpful feature of CrystalMaker as well. In this case, all of the atoms have the same coordination number, but if you have different atoms within the compound, you might have some variability to the coordination number. Now, within the provided information, there's a PDF that gives you information about the tutorials. There's different ones that you can look at. You can explore those if you want. I think that what I'm trying to do that can be helpful is to show you which subset of the ones that are freely available you might find useful. Gold is one example. Silver is very similar to gold. It's the same crystal structure. These other ones looking at graphite, diamond, let's explore some of those. So this is what I like with the graphite sheet one. So I'm going to open up that file. Let's get rid of the information on the right-hand side. So they're choosing to make it look with this particular representation. They're trying to have it say, oh, let us show you what one sheet looks like. But I'm not going to let the program boss me around. I'm going to generate my own supercell. So initially, this is what I'm starting with. Okay, that looks manageable. Let's scale that up. I'm going to unit cell, generate supercell. I'll make it even bigger in this case. Let's rescale that. This is a great one to rotate. Look how complex it looks there. It's very difficult to make sense of it. Let's keep it moving. And then almost like magic, look at the clarity we get when we see the sheets. That's sort of a wow moment. I'm going to zoom in a little bit. Go back to the hand and we can rotate on this one. Once again, it looks so complex, it's very difficult to make sense of it. And almost like magic, the sheets emerge. That was looking at graphite. Another one that we can look at is for diamond. So again, the designers here, they're trying to show us a particular feature of diamond, of how the stacking takes place in that. But we don't need to let that boss us around. We can explore it however we want to explore it. So we can spin this around. I'm going to make my own unit cell. Let's just look at the initial unit cell for diamond. That's our unit cell for diamond. Change the scale in a little bit. Now there's that text information there. I'm not loving that. Let's see, so I can move it. I can click inside of it. Okay, that allows me to delete it. That's what I want to do. Go back to the hand to be able to spin around the unit cell. If we want to look at the coordination for the carbon within here, let's go back to that idea of looking at a cluster. A cluster from when we move out from that central carbon atom to a certain number of angstroms away. That's 3 angstroms away. That's within 2 angstroms away. So those are all the nearest neighbors around the carbon atom in our diamond structure. Click on it. Yep, this would be the bond distance. It's equivalent from the carbon to all the other neighbors. Here's one that they have showing SiO2 when it's adopts what's called the quartz structure. What they're trying to show within this one is how the structure changes as a function of temperature. That's why they have the different crystal structures. I'm not particularly interested in that at the moment, so let's just grab one of them, take the unit cell, and just see what does the initial unit cell look like. Okay, that's a unit cell for the SiO2 quartz. If I click on this one on the right hand side, it shows me the atoms that are present. So the red, sort of the key. The red is showing the oxygen and the blue is showing the silicon. Let's expand that out. Look at more than just one unit cell. So SiO2 like this, pretty much a network covalent solid. I've mentioned the importance of being able to visualize the unit cell. This is a great one. This shows a translucent unit cell. That's just a fantastic way to show if something, a particular atom, is it entirely within the unit cell? Is it on the face sharing with a neighbor? What happens if it's on the corner? Outstanding way to show what does it mean to have a fractional contribution for an atom within a unit cell. Now this one is one that you can choose. This is for aspirin. This is in the program as a molecule, not as a crystal. Notice it's describing and saying that there's a certain number of atoms and they're all visible here. They're not saying construct the crystalline structure. It's just saying here's just what the molecule itself would look like. If you try to take this and generate the unit cell, it doesn't give you that option. The program does not have the data in this. It's just showing the XYZ representation of the molecule itself. So in a way, if it's listed only as a molecule, it doesn't have as much complete information. Now, one that's not listed, but you might want to use is sodium chloride. I didn't know if the program would have this functionality, because again, I'm getting as much as I can out of a free program. I did not think this particular function would be available, but it is, and this is huge. So watch this. What you can do is, instead of using the ones that are provided, you can decide to add a new crystal. This comes up and says, give me the information I need to construct a new crystal. The information, I list that over here for sodium chloride. This process right here that I'm going through, and you can do yourself, allows you to construct the crystal structure for sodium chloride. You first are choosing what's called the space group. You're giving information about the size of the lattice in angstroms. I'm just taking the information that's presented here. One of the atoms that will be present is the chlorine. It says that chlorine is at present at position 0, 0, 0. So within the program, I'm adding chlorine at position 0, 0, 0. To that, we'll now add sodium. Sodium is the other atom present. If I look at that, it's found at positions 0.5, 0.5, 0.5. So let's add that within our setup. This is about the simplest that we can have when we're constructing a crystal structure. And voila, sodium chloride. With this functionality within the program for free, we can now really just take the data and enter it ourselves for any crystal structure that we want. So this would be a great one that you can use for looking at an ionic compound like sodium chloride. We can look at it ball and stick. We can look at it space filling. This was the information for making sodium chloride. And by making it, I mean putting in the correct space group, the cell parameters, and where the atoms are found. And then this is what generates the crystal structure in the visualization part of the program. This is one, if you want to look back, follow the steps that I just did, that would allow you to make and enter this and use this within the CrystalMaker. Couple more things for you. So within here, this particular website, there's a lot of different databases that have different crystal structures. Look at what this one allows you to do. This one lists many, many different crystal structures. I'm going to choose this one involving carbon. They show examples of carbon when it involves sp2 bonding, examples when it includes sp3. I'm going to take you to one that I frequently show my students. I'm going to go down to cubane. Notice what this allows me to do. I'm going to click on Examine the Structure, and it downloads a file. That file, it opens automatically within CrystalMaker. It allows me to visualize cubane within CrystalMaker. I really like this as an example of a molecular solid, because it shows with a molecular solid we still have this symmetric repeating pattern. But importantly, we have this discrete molecule found. So this is one that I use to really illustrate what does it mean to have a molecular solid. If I tried to see what does it look like to expand it out, it didn't give me that option because it's showing all of the total atoms present. Within this website, when I clicked on that, it was giving me this XYZ representation. Here's one if you want to get a crystal structure. So this is from the American Mineralogist Crystal Structure Database. Again, there's a lot of different databases. If I go to this one, it's another one that's free to use. I'm going to put in a mineral I've looked at before called olivine. What's going to come up is the information that I could then type into CrystalMaker and generate the crystal structure like I did for the sodium chloride. It also gives me the option of downloading what's called a CIF file. I'm going to click on that. That's another file that CrystalMaker is going to be able to recognize. Here's our unit cell for olivine. One other aspect that I'm going to manipulate here. First of all, it's great because it allows me to generate a supercell. I can expand it because it has the information about what the unit cell is. It's not simply an XYZ file. Now, this is something I've studied before. I'm familiar with olivine. This icon here allows me to look at the bonding within it. I know there's bonds between silicon and oxygen within olivine, but not between the oxygen atoms. So I'm going to click on the representation there, what's being shown as a bond, and I'm going to delete that. Now the only bonds that are present are between silicon and oxygen within the structure. And that's what olivine looks like. Zoom in. Each of the silicon there are tetrahedrally coordinated. So these are two examples of free databases. The one on the left, I give the website for it. I found Cubane within that. And when I did examine the structure in that case, this website gives you these XYZ files. And so they're sort of like pictures that what you see is what you get. But the picture they give for the solid cubane, I think, is really helpful. Here's a website for the link for the American Mineralogist crystal structure database. Within this, you need to have information like the name of a mineral, the information that then is reported that they have on file. This is all the information that you could type in if you wanted to use CrystalMaker to construct what the actual crystal structure looks like. Or if you grab the CIF file and download that, CrystalMaker will recognize it automatically. So within this, I hope I've shared some information that might help you use CrystalMaker. I think it is a great free resource. It can be a little daunting initially, but I think by looking at some specific features like the ones I shared within this video, I think it can be a really helpful way to visualize these with your students. I usually use them as instructor-led demonstrations. I would have this information that I'm sharing on the screen. We're looking at together. I'm asking questions, very similar to how I would use a PhET simulation.